Hey y'all. Talking through some stuff last night during the help session, we started just a little bit talking about some of the homework problems and this Hess's law stuff. Now, first off, question two, you got the announcement that something is messed up about that. I think that question was intended to have ozone and formation of hydrogen peroxide in it, and somehow got edited out. Again, I stole that question, and I've got to go and talk to the professor that I stole it from and let him know that it does not work the way it is written. There's not a correct answer there, so do not sweat it. Just pick something and move on, and we'll talk through some more of that. But in doing that, we were talking about Hess's law, and maybe it doesn't make complete sense to everybody. So I wanted to do this supplemental video to try to help with making sense of that. So I'm going to walk through a different example, and let's see if this goes in a little better. All right, first let's talk a little bit about why the thing even exists. So the purpose of this principle is to find those things that are hidden from us. So I like using those delta H formation values that we looked up in Appendix G, and I kind of actually lean on those and use them for everything enthalpy that I need. But, honestly, where do we get those values? Somebody has to experimentally determine those values. So if you want to know what the delta H of that hydrogen and oxygen in a bomb calorimeter is, well, you can put some hydrogen in there and with the oxygen and light it off and see how much the water heats up, and you can tell. You could do the same thing for graphite, even put graphite in a little cup in there with plenty of oxygen, light it off, make CO2. You can tell. But if I want to know, let's say for methane, CH4, I want to know the delta H formation. Well, so I would like to say from pure substances, right? In this case, well, we've got carbon in there and we've got hydrogen. So let's use carbon in the form of graphite and hydrogen in the form of hydrogen gas. And this is the way that the equation would be set up in a heat of formation appendix. Unfortunately, if you put graphite in your bomb calorimeter and charge it with hydrogen gas and try to light it off, you'll get something, but I mean it'll react, but it's not going to give you methane. It's going to give you some complex, horrible organic soup that you're not going to be able to tell anything about, because it turns out that we need life. We need proteins and bacteria to cause fermentation of methane. Methanogenesis is what it's called. We can't just do that very easily. Apparently, there's some planets or solar systems that this might happen in. There's a big debate about formation of organic molecules from abiotic processes. But regardless of whether it can happen at all, it certainly cannot happen easily in a bomb calorimeter. So we need a way to determine the delta H for this reaction right here, and we can't just do it. We can't just do the reaction to see. So the point of Hess's principle, Hess's law, is we can sum these up from other bits of information. So we're going to add up bits of other reactions to make this one. So we're going to use the formation of water from hydrogen and oxygen, because if you put hydrogen in your bomb calorimeter and burn it in oxygen, you get water. Okay, cool, we got that one. And then if we burn graphite in oxygen, yeah, we can get CO2. So that one happens. Okay, cool. And then we'll use another piece that's the burning of methane in oxygen. So it's kind of backwards, right? But we'll use it backwards in order to calculate the thing we're after. And I'll show you that on another slide. Okay, so we can't form methane in the calorimeter, but we can burn methane in the calorimeter. We can take and we can charge CH4 gas in a calorimeter, and we can put in O2 gas, and we can light that thing off, and it'll change to carbon dioxide and water vapor. All right, cool. And we can get a value. We can get this value of negative 890.3 kilojoules for that reaction. It's a very energetic reaction. But wait a minute. It's backwards. So what we do is we flip it around. Okay? So essentially I'm going to multiply the equation by -1 and flip it. So what I mean by that is if methane burning in oxygen releases 890.3 kilojoules, the negative here means releases, right? Then theoretically, if I could go backwards, I can't, but if I could go backwards, then we should be able to say that CO2 plus 2 H2Os absorbs the same 890.3 kilojoules in the reaction. So if I multiply my reaction by -1, then I reverse it. So CO2 plus 2H2O now on the reactant side yields on the product side CH4 plus 2O2, and I reverse the sign of my delta H. So now instead of negative 890.3 kilojoules, it's positive 890.3 kilojoules. All right. So right now, and I color coded this in red, and it's going to be on all the slides following, and then we'll stack things up as we go. All right. Okay. Now here's what we had in red down here from the previous slide. But now we can do the burning graphite thing. If that'll work in a calorimeter, we get a good clean negative 393.5 kilojoules out of it. Here's our equation. Oh, okay. Well, that looks good. So what I want to do is I want to stack that on. I made it blue, and I want to stack it on this one. And so what I'm leading to here is I've got CO2 on the left. The blue equation now gives me a CO2 on the right, and we're going to use that to cancel it out. And so what I'm looking towards in the future is being able to cancel out pieces of this reaction. Okay? And I'm just keeping up with my delta H's over here on the right. And we have this final step of the hydrogen. All right, so we can burn hydrogen in oxygen and make H2O. We get a good delta H of negative 285.8 kilojoules. All right, so that works. But let's look down at the bottom first. In red, do you see that 2 H2O that we needed in the methane equation? The green up here would only give us one of those H2Os, but that's simple to fix. We just multiply everything by green. So we've got our starting equation for formation of H2O. We multiply that whole thing, and that includes, very importantly, that includes the delta H over there. We'll multiply everything by 2. So, distributing here, let's change the pointer so I'll actually draw on here. So I am going to distribute that to the H2. I got 2 H2s there. I'm going to 2 times 1/2. Well, 2 times 1/2 is just 1. All right, so good. I got 1 O2. And then 2 times the 1 that I didn't write in there in front of the H2O. All right, 2 H2Os. And now, importantly, I've got to remember to multiply here also, right? And so I get this 2 times negative 285.8 is negative 571.6 kilojoules. All right, so see how I started with the red, I added the blue to it, and now I've added this green to it. The reason I wanted the 2, and this will come up in the next slide here, is because I've got a 2 right there, and I'm going to need that. Okay? All right, another step to go. All right, we stacked all those things up. Now what are we going to do with them? So we can just sum up reactions. And this was the thing that Hess was talking about when he formulated this principle. We can just sum up these reactions because just like we talked about in class with, I don't know, was it Henry and Josh that got to the top of the hill there? It didn't matter how they got there. They ended up at the same elevation. So Hess says it doesn't matter how we get to those products. The delta H's will be the same because they're a state function. So I'm just going to draw a line under there, and I'm literally going to add all these things together. Okay? So, and I kept the color coding. So here's my 2 H2s go here, right? So let's go back to the pointer options here. So my 2 H2s came and got down here. Let's see, I've got a green O2 there. I'm put it here. Okay? And then I added my blues in, right? There are my blue ones coming into the O2s. But I have to do these on the, so my product arrow here, right, I've got two H2Os, two CO2s, and then the red that we started with earlier, I've got reactant side here, CO2 plus two H2Os, and I got product side, CH4s plus two O2s, all right? Now, what I've done here is I've said, wait, I don't know, what is this delta H going to be? I hope some of you see where I'm going to go with this, right? Okay, what's next? All right, I'm going to start canceling. Look at that. So those two H2Os and those two H2Os, well, I've got two H2Os on the reactant side. I've got two H2Os on the product side. Hey, I don't need those. They'll just cancel out of my reaction. I can just ignore them. Anything else we can cancel? Let's see. How about CO2s? They cancel, right? Those are gone. Great. The O2s. Now look at the O2s. I've got one O2 here, and I've got one O2 here. That's two total. Hey, look at that, two over there. So those two O2s cancel those two O2s. What do I have left? I've got this carbon right here, and I've got this hydrogen, two of them left right there. So we got this, we got this. Everything else canceled out over here. On the product side, looks like everything is canceled except for my CH4 right there. So I've got this much simpler equation now by canceling all that stuff out. So I hope that you see what we can just do with our summation. Since we added all those reactions together, we're just going to add, literally add, all of these delta H's together. So negative 571.6 plus negative 393.5 plus positive 890.3, and I get negative 74.8 kilojoules when I add those together. Then it turns out if you go and look in your in Appendix G of your textbook, you'll see that that is exactly the delta H listed for methane from carbon and hydrogen is negative 74.6 kilojoules. Well, it turns out that this is how we experimentally determine this value. All right, so that's the whole point of doing Hess. And I don't know, maybe it was cryptic the way I said it originally. I don't think I spent a lot of time on it in lecture. Maybe it was cryptic the way the book put it. And if this helps clarify it, maybe it'll help with the homeworks. Let me know what else we need to talk through on this. Give it a shot using this idea here.